Let's try out our trick for solving separable equations on a few examples. So here's one example. We're coming back to our temperature example. So we have an object that starts at 40 degrees centigrade and cools in a 20-degree room, and that gives us this differential equation. So we saw where this equation comes from. It just comes from Newton's law of cooling. So the question is, how long will it take for the object to cool to 25 degrees? So to answer this question, if we can find the temperature function as a function of time, then this question will just be a matter of solving, right, setting this function equal to 25 and then solving for t. So all we need really is, the hard part is going to be finding this temperature function. But this equation is a separable equation. It's a separable equation because there's no little t in this equation except in the dt on the left-hand side. And so it is some function of little t times some function of capital T. So this counts as a separable equation. So let's do our separable equation trick with it. So d capital T d little t equals minus 1 over 10 times t minus 20. So first part is to get the part of this function, the part of the right-hand side with capital T over to the left. So we're going to divide both sides by capital T minus 20, like this. Notice I sort of have a choice for whether I want to consider this minus 1 over 10 as part of the little t function or the capital T function. And I'm just going to leave it on the right-hand side, so treat it as part of the lowercase t function, just because that's how I feel today. Okay, the other part of separating the variables is we need to get this d little t to the left, so we're going to multiply both sides by d little t, like so. So on the right-hand side, the t minus 20 is gone, and on the left-hand side, the dt's are gone. So now we have 1 over capital T minus 20 times dt equals, and then on the right-hand side, minus 1 over 10 d little t. And now we can integrate, right? We've successfully separated the variables, so now we can integrate. On the left-hand side, integral of 1 over capital T minus 20 dt is natural log of capital T minus 20. On the right-hand side, integral of minus 1 over 10 dt is minus 1 over 10 times t. And remember, we need a constant of integration somewhere, and usually we'll put it on the right. And then finish solving for capital T, so we need to exponentiate here. So the exponentiation base e and the natural log base e undo each other, and on the left we're left with t minus 20. And on the right we have e to the minus 1 over 10t plus c. But right, we can simplify this. This is e to the minus 1 over 10t times e to the c. And again, we'll say that introduce a new constant of integration a, which is just e to the c. So now we have t minus 20 equals a times e to the minus 1 over 10 times t. And then add 20 to both sides. So capital T is a e to the minus 1 over 10t plus 20. Okay. So there's our family of solutions for the differential equation. And as usual, it's a one-parameter family of solutions because there's this constant a that came from the constant of integration. Remember, we have an initial condition. The object that's cooling down starts out at 40 degrees. So 40 is T of 0. And if we plug times 0 into our formula for capital T, we get a times e to the 0 plus 20. And so e to the 0 is 1, and so we can solve this for a. Right, subtract 20 from both sides, it looks like a is 20. So our temperature function, capital T of little t, is 20 times e to the minus 1 over 10t plus 20. All right, now we have our temperature function. We wanted to know when is the temperature 25 degrees, so now we can just set this equal to 25 and solve. So 25 equals 20 times e to the minus 1 over 10t plus 20. Subtract 20 from both sides. 5 is 20e to the minus 1 over 10t. Divide both sides by 20. 5 over 20 is a quarter, so 1 over 4 is e to the minus 1 over 10t. Now take natural log on both sides. Natural log 1 over 4 is minus 1 over 10t, and then multiply both sides by minus 10, and we get minus 10 natural log 1 over 4. And we can dump that into a calculator if we want to know how many time units that is. Okay, so this separation trick really worked with this temperature equation, and it would work with any autonomous equation since every autonomous equation is separable. Let's look at another example. Okay, let's solve this differential equation. Notice that this differential equation is written in this sort of differential style. Sometimes this differential style is more convenient just kind of depending on the field that you're working in. One thing that is nice about this differential style of writing a differential equation is it makes it pretty easy to separate the variables if it is a separable equation. So if you look at our dx term, only x's show up in that term, and in our dy term, only y's show up in that term. So we can completely separate the variables just by moving the dx term to the right. So we get y squared plus 1 times dy equals x squared minus 1 times dx. And now we're in a position to integrate. So on the left-hand side, we get 1/3 y cubed plus y. On the right-hand side, we get 1/3 x cubed minus x plus a constant. Remember, since both of these integrals up here are indefinite integrals, we need a constant of integration somewhere. So we've done the integrals. Now, if we could solve this equation in some convenient way, we would, because we like an explicit solution if possible. But this equation isn't going to have a nice explicit solution, right? I guess if you happen to know the cubic formula, you could use the cubic formula to get an explicit solution, but that's going to be pretty messy and probably not very informative. So we're going to leave it right here. We're going to just accept that the nicest way to write a solution for this differential equation is as an implicit solution. Okay, one more example. So here's another autonomous equation. And autonomous equations, we saw we can always separate just by dividing both sides by everything involving the independent or involving the unknown function. So divide both sides by y minus 1 times y minus 3. And also, while we're at it, multiply both sides by dx. Okay, so on the left-hand side, we're going to get dy over y minus 1 times y minus 3. And on the right-hand side, we're going to get just dx, it looks like. Okay, now we need to integrate. The integral on the right is no problem, but the integral on the left, oh, that looks unpleasant. One thing that happens when you're working with differential equations is you have to have all of your integration tricks ready because you never know what sort of integral is going to show up when you're trying to solve a differential equation. This particular integral, right, integrating 1 over y minus 1 times y minus 3 dy, this is an integral we can do, but there's a trick for it. Right? The trick is called partial fractions. What we need is the partial fractions decomposition of 1 over y minus 1 times y minus 3. And so if you go back in your calculus textbook and review partial fractions, you'll see that we can write this as some constant over y minus 1 plus some other constant over y minus 3. Now if we clear all the denominators in this equation by multiplying by y minus 1 times y minus 3, this equation turns into 1 equals a times y minus 3 plus b times y minus 1. And this equation is supposed to be true for every value of y. So in particular, if we plug in y equals 3, this equation turns into 1 equals 2b. Right? The a term goes away because 3 minus 3 gives you 0. And this means that b is a half. And if we plug in y equals 1, this equation turns into 1 equals minus 2a, because the b term goes away, because we were getting b times 1 minus 1. And that means that a is minus a half. Okay, so coming back to this integral, we can integrate, right, we're replacing the integrand with this partial fractions decomposition. So it's a, which is minus a half, over y minus 1, plus b, which is a half, over y minus 3, all of that times dy, equals, the right-hand side, we can do this integral. Integral of dx is x plus a constant. Okay, now calculate the integral on the left. So we got minus 1/2. Integral of 1 over y minus 1 is natural log of y minus 1, plus 1/2 times integral of 1 over y minus 3 is natural log of y minus 3. And on the right-hand side, x plus c. Okay, now we can multiply everything by 2, maybe, just to get rid of the 1/2s that are lying around. So minus natural log y minus 1 plus natural log y minus 3 equals 2x plus 2c. But remember, c is an arbitrary constant. And if you multiply an arbitrary constant by 2, it's still arbitrary. So let's, instead of writing 2c, let's just write c. Or maybe c, you might want to decorate this c somehow to indicate that it's different than what it's a different version of c than what it used to be. So maybe give it a subscript or a hat or something like that, just so you know it's different than it used to be. Okay, now we're trying to solve this for y, and we have two natural logs with the same base that are being subtracted. Well, we can put those together. We can use the laws of logarithms. So we get the logarithm, natural log of, let's see, the one with the plus ends up in the numerator, so y minus 3 over, then the one with a minus ends up in the denominator, so over y minus 1 equals 2x plus our new version of c. Now we need to exponentiate to get rid of this natural log. So the exponentiation base e and the log base e undo each other. We get y minus 3 over y minus 1 equals e to the 2x plus c hat. But right, as usual, this is e to the 2x times e to the c hat. But we can write this as a times e to the 2x. This a is different than the one from partial fractions. So we're making progress. We just need to finish solving for y. Right, at this point, we've solved the differential equation. We're just doing all the algebra to get an explicit equation. Right, at this point, the calculus part of the problem is done. So, but let's run through the algebra just to finish everything off. We need to get these two appearances of y together to one appearance of y. So let's, I guess, maybe clear the denominator. So multiply both sides by y minus 1. We get y minus 3 equals a e to the 2x times y minus 1. What we're going to want to do is get all of the terms with the y to the left-hand side and all of the terms without a y to the right-hand side. So we're going to have to multiply out this stuff that's on the right-hand side. So y minus 3 equals a e to the 2x times y minus a e to the 2x. Now we can take our y terms to the left and our constant term to the right. We get y minus a e to the 2x times y equals 3 minus a e to the 2x. Okay. Next, I guess on the left, we can factor out that y. We get 1 minus a e to the 2x times y equals 3 minus a e to the 2x. You see, we've successfully collapsed the two appearances of y down to one appearance of y. So now we can just isolate this appearance of y. We get y equals 3 minus a e to the 2x over 1 minus a e to the 2x. All right. And we did it. We solved the differential equation. Remember, the differential equation that this all came from was dy dx equals y minus 1 times y minus 3. And we have this one parameter family of solutions for this differential equation. Notice that this differential equation, since it's autonomous, we can find equilibrium solutions just by setting this equal to 0. So 0 equals y minus 1 times y minus 3. And that gives us two equilibrium solutions. There's y minus 1, or sorry, y equals 1 and y equals 3. Okay. And if you look at these two solutions and compare them to our one parameter family of solutions up here, the solution 3 shows up when a is 0. Right. Remember, this one parameter family of solutions, you can choose any value for a, and this will become a solution to the differential equation. And if you choose a equals 0, then this turns into y equals 3. So this equilibrium solution 3 is part of these one parameter family of solutions. But what about this solution 1? It looks like there's no number you could plug in for a in our one parameter family of solutions to make this just the constant 1. But actually, it's true that y equals 1 is not in this one parameter family of solutions, but it's a limit. If you take a limit as a goes to infinity, then it turns out you get 1. So the other equilibrium solution isn't really part of this family, but it's a limit of this family.